we are starting. So as usual, we will do the C++ session first. Why don't I do one thing? Before I start, I will give you, do you have access to practice lab 4? Last class. I would like you to start with that, then I will tell you what to do. If you have practice lab 4, just let me know if you have practice lab 4. And you can open it and see the code that we have written in last class. Yes? Just check in your list. Otherwise, open this practice lab 5. You should see what code we had done in the last class. At least let me know quickly whether it is there so we can start. Practice lab 5. Does it have the code? Okay, good. So, yeah. So please, we will use practice lab 5 as our basic code today. And today what we are going to do is, we are going to do something interesting with lists. So, in the last semester, I guess, we had done C, right, last semester? Some of you had done, I think, depending on what branch you are. So, you must have been familiar with this word recursion. Yes, no? Now, one important thing is, in computer science, if you don't understand recursion like the back of your hand, you can never become a good computer science engineer. So we are going to start in this session. I'll keep giving you more and more questions on recursion. Recursion will work on linked list, recursion will work on trees, recursion will work on graphs, recursion will work everywhere. So you have to understand recursion and be able to write any problem or many problems in a recursive solution without thinking too much. So I will also tell you, recursion takes a little while to get the hang of it. Some of you will get hang of it right away. Some of you will take a little bit of while. So have patience, it will come. Because in these years I have seen, and it does not mean that you are not going to get it. Once you get it, you get it. Okay? So, those of you who don't get it at the first go, don't get yourself demoralized. It will come. Believe me. Trust in me. It will come. Just you have to keep your cool and keep doing. It will come. It always comes. Okay. Only thing is, a bit of effort is required. So, I will briefly give you an overview of recursion because maybe some of you know, some of you don't know. And then we will start doing some of these questions using recursion. But one thing, when I say do it with recursion, please do it only with recursion. Don't show your skills by going through the list. You have to, that's the only way to learn. No value for solving a problem. You have to solve it using recursion. So all problems we are going to do today, we are going to solve on linked list with recursion. Okay, we are not going to use our regular traversal in the list. No, we are not going to do that. Okay, so maybe a quick summary of what recursion is all about. I'll basically maybe revise what is recursion. What is a secret or what is a one-line answer of recursion is, if you are given a problem with size n, if you are given a problem for size n, you have to see whether the solution for a problem of size n is dependent on the solution for a problem with size n minus 1. It could be n minus 1 or n minus 2. That means, can you solve a larger problem by solving a smaller problem using a similar algorithm and adding something to it or multiplying it with something? So, is it possible to use the solution of a smaller problem using the same algorithm which you have used for n and then solve the problem? So, it is like saying, by reducing the size of the problem and combining that problem solution with something, can you solve a bigger problem? That is all it is. So thus the solution of n can be derived from the solution of n minus 1 with something more. Okay? Can it be done like that? Any problem, and you will see and we will demonstrate today, all the problems or almost all the problems that we have done so far, all can be solved in a recursive way, and we will demonstrate how. Okay? So let's go step by step and understand this. So I will give you the traditional example, but say it in a slightly different way, and then we will say how recursion works. Okay, let me take you to the next page. I will take the traditional example of recursion, which is the good old factorial. Okay. Now, I don't think here we have to talk about what is factorial. If I tell you that, then you don't need to be there. So the factorial of n, of any number, can the problem be solved using a smaller range of numbers? Can the factorial of 5, can it be solved using factorial of 4 by reducing the size of the problem? So yes, it cannot, it can be. So if I have factorial of n minus 1 with me, okay, if I have the factorial of n minus 1 with me, if I multiply that with n, or n is multiplied by the factorial of a smaller problem, then that will yield to me the factorial of a larger number. So by taking a problem, seeing whether I can use the same algorithm to solve a smaller part of the problem, assuming that I have the solution for the smaller part of the problem, can I build a solution for this problem? Which is like saying, can I build a factorial of n using factorial of n minus 1? And what should I do if I have the factorial of n minus 1? What should I do in order to get the factorial of n? Anybody will tell you? I have to multiply n into the factorial of n minus 1. Correct? So that is how factorial of n. And in any recursive problem, the other thing is, what happens when n is 1? Okay. Or n is 0, depends on how you take it. For n is equal to 1, I may not want to do n minus 1, or maybe n is equal to 0, I don't want to do n minus 1. That means the problem will reach a certain point where the size of the problem, let's pretend it is n is equal to 1. I don't want to decompose the problem further. I don't want to do factorial 0. I instead want to say return 1. So if n happens to be 1, I want to terminate the recursion, because I don't want to go and use a smaller size of the problem. I have reached the minimum size of the problem. I don't want to go further down. That is, I don't want to reduce the problem some more. So what will I do at this stage? I will not use recursion. I will simply say return 1. End of the story. I will simply say return 1. Done. That is what I do. So that is how I write a factorial. So factorial of n is, if n is equal to 1, return 1. If n is not else, I say n into factorial n minus 1. Very trivial, very simple. What is the secret sauce here? That I have converted an n problem into an n minus 1 problem. Okay. If you know, and I am sure you have done maths at some stage, maybe 10 plus 2 or 10 plus 1, I don't know. You must have heard about the principle of mathematical induction. No? Does this word sound familiar? Somewhere in your intermediate study you would have encountered the word principle of mathematical induction. What does the principle of mathematical induction say? That if you know the solution for n equal to 1, okay, and you know the solution for n minus 1, then you know the solution for n. Mathematical induction principle is what? I know how to solve this problem for 1, n equal to 1. And I also pretend that I know how to solve the problem for n minus 1. Then using these two, can I create a solution for n? That is what, and the principle of mathematical induction says that yes, you can do. You can always express the solution for n using the solution for n minus 1 and n equal to 1. If you see, Isn't that a very close association between that and what I have written on the board? It is more or less what I am saying, isn't it? I am saying, you know the solution for just a very small n, tiny n, where the solution becomes trivial, where you don't have to solve it. And then you know also how to express a solution for n using the solution of n minus 1. If you know that, you can solve any problem. And that is the power of recursion. Okay. That is the easy part. This I think everybody will understand, appreciate and follow. Now, let's take a common problem. Let's take a linked list. Okay. Right? So, let's write a very simple function which you already written called display. Display on a linked list. What does it do? What is it supposed to do? What did you write? You wrote, it takes a root pointer, it takes the head pointer, and then goes from while hptr not equal to null or something like that, or you say temp is equal to hptr because you don't want to disturb the head pointer. You say while temp not equal to null, call display on temp and move temp to the next line. Say temp is equal to temp next. That's how you have written it without using recursion. That is a non-recursive solution. Can you write a recursive version of that? Yeah. How will you do it? Very easy. So let's make an attempt to write a recursive version of display. Okay. For some of you initially, some of you will take it very easily. Some of you will take a little while, but we will get there. So there is already a hptr, remember, in the linked list. So we are called display. Display on the linked list. How will we write it? Using recursion. So I will say same way. If let's say as usual temp is equal to hptr, because I don't want to disturb as usual hptr. Now when I am working, now here what is the equivalent? When my list contains only one node, that is the trivial solution. When my list contains one node, you ask me to display that list. What will you say? I'll just display the data in the list and I'm done. Simple enough. I just have to show one node. When does that happen? When does the trivial solution happen? When my list contains just one node. Or I'm assuming if the list contains no nodes, you just return. Let's keep that trivial solution aside. Let's keep that aside. You can have that also. But let's take a more sensible trivial solution where it thing consists of only one node. How do you know you have reached that point? That you have reached the trivial part of your problem. How do you know? When temp's next is none. That means my list is a single node list. You agree with me? So when I have reached that point, I know for sure my list contains only one element. It's a trivial solution. I just have to output the data and I am end of story. Let's write that. Let's write the trivial part first in our display. So I will put a if condition. If temp, if temp next equal null. My next is null. Okay. That means I have reached the trivial part of the solution. I simply say cout temp's data. If I am writing on different lines, I will say endl, or if I am writing on the same line, I will put a space after it. Does everybody buy this? Let me write now the else. Is everybody clear so far? I have not done anything. I am just writing a display. I have just taken care of course, temp is equal to hptr because I don't want to play with hptr. I have said, if my problem has reached the trivial part, or my problem is a trivial one, I have to learn how to identify the trivial problem, which is my temp's next is none. That means I am asked to display a list with just one node. So I solved it. Yes, everybody with me? Okay. Now, else means Temps next is not null. That means it's not a trivial list. It is a list with a few nodes or more nodes. Correct? So, in that case, what should I do? What should I do? Remember the basic philosophy of recursion. That I have to reduce the size of my problem every time by something. Maybe here by one node. Okay. So, let me write it. And then you tell me whether it will work or not. So, else means my list has some nodes, not just one node. Then what will I do? I will say, as usual, cout temp data enter. This is one line. This will show which node? The one where temp is pointing to right now. Correct? It will show that node. Everybody agree? Then what will I say? Display. Remember, I have to reduce the size of the problem. How do I reduce? Solve one node and let the same algorithm now crunch its teeth on the remaining part of the list. So, display. What will I say? So, now what I have to do is, if I am using the display that way, I have to advance my head. Otherwise, it won't work. So, I will have to change my display to take a pointer. Let's change it to take pointer. So, I don't have to do this. And it will be called with head. I'll write another display which takes a pointer. I'll change it a bit. So, it checks which is the head of the list. So, now I will say display. I'll change it a bit. Display. Whatever pointer I have received, temps next. That's it. This is the recursive version. I'll maybe type it. Then I can show you that in a neater way. Okay, my display I have changed it a bit to make it recursive. Display will take a pointer as a parameter. You can have the old display and you can write a new display also in your thing. You don't have to corrupt that, because let that work. We'll write another display which will have this parameter. Let me now write it for you and then I'll show you. Okay, we'll write it in front of you and we'll play it in front of you. So, let's create another display method in that class. Somewhere at the bottom or somewhere. Below that display, so void display. My display now takes a parameter of type node star. So we are writing there. So void display node star temp. So it always takes a pointer. First time it will take the head pointer, obviously, and it will work with the head pointer. So what it will do is, if temp next, that means I am given a list with just one node. This is what it is. If temps next is equal null, what I have to do? My list is of one node. I think that everybody understands. We have to just display that one node. Okay. Then else. Else, what it means? My list has at least two nodes. It can be two or more nodes. It just doesn't have one node. Does everybody agree with that? So, now I have to reduce the size of the problem. How do I reduce the size of the problem? By what quantum am I reducing the size of the problem? By 1 unit. Let me pluck one node out and reduce the size of the problem. Do you agree that I will reduce the size of the problem by taking one node out and using the same algorithm on the rest of the list? The algorithm will remain the same. The way I display 10 nodes, think a little. The way I display 10 nodes, will the algorithm change if my list has 9 nodes? No. The mechanism I use for displaying 10 nodes, is it not exactly similar to the mechanism I use for 9 nodes? I think everyone will agree it is same. Can't change. So I am using that concept. So I am saying, C out, look at that, look at the else part, just that much. Else part, C out, temp data. That is currently temp is where? Temp is on the first node. So I am displaying temps data. Done? Then I will say display again, but this time what will I give to display? Temps next. I will give temps next. What is temps next? If you visualize what is temps next, I will say it is the head of a new list which starts from the second node. Would you agree? Temps next. I am at the first node of a 10 node list. So I have displayed the 10th node. I have displayed the first node. How many nodes are remaining? 9. Where does that list start? At the second node. Would you agree? The list starts at the second node and goes to the end. So, am I not using that? If you look at line 104, I am having C out temps data. That is, I have taken care of the first node and I have now taken care of the remaining list by saying, now you go ahead and use the same display algorithm for the remaining part. What is the remaining part? It starts with temps next. That is the head of the remaining list. That is how it will progress. That is how it has to progress. So have I not used the law of mathematical induction? Have I not used that solution for n minus 1? Have I not used solution for n equal to 1? I have. And I just said reduce the size of the problem and let the system do that problem. Now what will happen? When I call again, this function will be called again. It will call with 9 nodes. So 9 nodes, what will happen? It will display the first node of that 9 nodes, which is actually of the main list, the second node. It will display that and call the same algorithm for remaining 8 nodes. Agree? Not agree. Then when I am calling it with a list of 8 nodes, it will display again the first node in those 8 nodes and call display for the remaining 7 nodes. Like this it will go on till the list has only 1 node. When the list has 1 node, it will not go to the else part. The same code will be called again. It will not go to the else part. Instead it will be tackled in the if part. And in if part, if you see, there is no more recursion. I have terminated the recursion. Look at the if part. In if I am not propagating the problem, right? Because I have no smaller problem to solve. I have done. This is the end of the story. If my list consists of only 1 node, end of the story there, no? Where is the need to solve anything else? When I have more than 1 node, then I solve the first node, that is I display the first node, and then I proceed with the remaining list. You agree? Okay. Will this work? It should work, no? No, we'll have to call it at some stage. L.display, we'll call it L.display HPT. No? Needs a pointer. So first we'll call it with HPTR and then it will go recursively. HPTR is anyway available. No. You can't say HPTR in main. You have to say L dot. Okay, I hope you understand that. Linked list itself has a HPTR. Oh yes, it has a field in the linked list which I am using. L dot HPTR means go to the linked list, get its HPTR, that becomes the first pointer. So I am using L dot HPTR. Let's try. And because L is a linked list and not a pointer, new display. Just put a line, new display. Recursive display, very good. Okay. So we run it. Yeah. You can see the recursive display it's producing. If you can make it a little bigger. Yeah. So you see there, the just above the recursive display is the old display. Same thing in the linked list. Don't worry what data is there on the linked list. Whatever is the data on the linked list, the recursive display is producing the same answer as the earlier display. So it is working. Now I want you to think a little, look at that code and think a little. What did we do? So the code is in two parts, if you see. Like any recursive, the code will have two parts. One is called identification of the termination condition. Termination means where recursion is not going to happen. That means you will reach a very trivial state of the problem. That is called the terminating condition. How do you identify that? If you look at the code, you can identify the terminal condition by saying where recursion doesn't progress. Okay? And there will be an else part or another part of the code where you will solve part of the problem and call the same algorithm. That is why it's called recursive. For a smaller problem. And smaller problem becomes still smaller and becomes still smaller till it reaches a trivial solution. And then the trivial solution gets built up and gives you the answer. That's how recursion works. So you have to drive the solution towards a trivial solution. And once a trivial solution appears, it's like if I know how to display two nodes, how do I know how to display two nodes? By displaying one node. First node, just imagine you have a list of two nodes. How will it work with recursion? It will display the first node and call display on second node. Second node will be a one node list. There it will terminate. So imagine you have a solution for two nodes now. Can it be used to solve three nodes? Yes. Three node, the first node and the third node has to be taken directly and then use the solution for two nodes, which will use the solution for one node indirectly. Correct? So that's how it will get built up. Did all of you get the hang of recursion? I hope not yet. Otherwise, the whole session we are going to get, because we are going to do different sums and understand how to do recursion. As we go, we'll develop it. End of session, believe me, you will understand primitive recursion. Okay? And then recursion will not leave us till you are in fourth year or third year. Okay? And we'll do various styles of programming with recursion. It will take moment you understand recursion, actually you are ready to go. Okay, completely. And its full glory. Complex problems, ability to solve them recursively. Okay, now let's try another thing. Okay. Now it's a linked list of numbers, right? In our case, it's a linked list of numbers. All our data are integers. Now, you have done sum somewhere, sometime, correct? Somewhere we did, no?
Yes, sir.
Maybe it's there here or maybe you have done it. How did we do sum? In the same way. You created a variable called sum equal to 0. Started the list, started from the head, went crawled till the end. Whatever value you had, you went on adding to the list. Yes? Sorry, adding to the sum. And at the end of it, when you reach the end of the list, whatever sum had, that was your answer. Okay. Now, can you do sum recursive? Correct? Easy, no? What is sum of nodes in a list? I said, what is the philosophy of recursion? Reduce the size of the problem. Correct? So, sum of 10 elements is sum of 1 element plus sum of 9 elements. No, yes. I mean, anybody will tell you, no. You have 10 numbers. The addition of 10 numbers can be obtained by taking the first number and using the same algorithm on 9 numbers. And the sum of 9 numbers can be arrived at by taking the first number out from that list and doing the sum of 8 numbers. Till you reach a terminal condition where there is only one node. When one node is there, what is sum? That, whatever that value is, that's it, no? If you are given a list of one number and said, give me the sum of all nodes in the list, you will say, whatever the value of one node, that is your trivial condition where you don't need recursion. Okay. So, now, again, assume a sum with a HPTR. We'll pass a pointer. So write a sum, try to write a sum first. Sum with what? It should return an integer. Agreed? And it should take a pointer as a parameter. So write a sum with that. Try it. Sum with parameter. Node star. So you write this sum. Node star 10. And please use recursion. Don't use loops. Don't write a for loop. No for loop. For loop means you are not using recursion. For loop or while loop. No loops. Okay. When you are reaching the end, you are doing the display. No, you just have to return. Change it a bit. Just return it. You are printing it, don't print it. Return it. Then we'll move on. Okay, we'll show the solution for this. We'll do the solution for this. Now the initial parts we are going to do. So we'll start with int sum equal to 0, obviously. And what will we do? So as I said in recursion, first the trivial part. When is the solution trivial? When the list consists 1 node. So what will I do in that case? If first identify that case. How do I identify that case? Temps next is none. There is also the even more trivial case where temp is equal to none. I'm not handling that, but you should. Temp equal to none, what will you do? Return 0. No, yes. If the list is empty, there is no sum now. So you can take care of that. Another trivial case. Sometimes there are more than one trivial cases. Just like even in factorial. Factorial of 0 is also 1. Factorial of 1 is also 1. So you have to take care of both. But I mean, as long as you can identify the trivial cases, we don't mind. So if temps next is equal null, then return temps data. Okay. Does everybody get this part first? No, yes. If my list consists of 1 node, you are with me? If the list consists of 1 node, what will I do? Return data, no? What is the sum of 1 node? If I give you a node with one node in, give you a list with 1 node in it, and ask you what is the sum of nodes in a list, what will you say? Whatever the value sitting there is a sum. So that return temps data. Done. Else means what? My temps next is not null. That means there are more than 1 node in my list. Agreed? No? Yes? Agreed? Now, what will I do? Else. I will now say, for the reduced list, what is the sum? Remaining list. For the remaining list, what is the sum? Plus, whatever is the sum in this node. Correct? That will be the sum of the list. There are more than 1 node. So, I'll take the 1 node out and get sum on the remaining list. Whatever that returns, plus this node, is the sum of the entire list. So, again I am reducing the problem by one step, taking that value out, using the same algorithm to compute the sum of the remaining list. So, how will I do that? Else, I will say, return, I'll try to write it in one line, or you can use sum. I don't want to use sum. So, return temps data plus, can you complete that for me? Return temps data plus sum of temps next. You agree? Remaining. Let that guy do it. Some knows how to sum a list, no? So let him work for me. Finally it will go on and the sums will be built up. So sum temps next. Now, I don't need a return. That 116 can go. If as a return and else also as a return, so I don't need a return there. So, you got me? What am I doing? If I have a 9 node list, I am saying I'll take the 9th node out and try to get the sum of 8 nodes. 8 node list, 8 node out, sum of 7 list. It goes on till I have 2 nodes. 2 node, second node out, sum of 1 node list. That it knows how to solve. And it will not go further. It will just return that value. That I will add to 2 node, I will get the sum of 2 node. That will go to the waiting sum for 3. See, the sum for 3 nodes will not finish till, this is another thing you should understand. It's like you're breaking a problem down, and till the lower problems finish, the upper problem won't finish. Okay, I think this may need a little thought, not too much thought. So when I say return, just look at this line, return temp data plus sum of temps next. So let's say initially the list has 5 elements. So this is the first element and these are the remaining 4. So this is going to then result in second node and the remaining 3 nodes. So 3, 4, 5. So this is going to result in 3 and 4 and 5 separate. So this is dependent on this is dependent on this, and this is 4 and just 5. This will return for immediately because it's a single node list. It will say the answer for this is 5. Then this is what the sum of this is 4 and this, right? 4 and this. What is the answer of this? 9. So this will give 9. Then this is 9 plus 3. That is the answer for this, which is 12. So this part has been solved. The sum of that is 9. And then it will combine this solution and come back. So at every stage, it will come back. And the sum of 4 nodes in a list cannot be solved without using sum of 3 nodes, which cannot be solved using sum of 2 nodes, which is solved using sum of 1 node. So that's how the thing builds up. Okay. So how many of you could finish it using recursion? Not yet. Not yet a whole lot. Okay. Did you understand when we wrote sum? Did you understand now? When we created our sum? Okay. As I said, it takes time. Let's do one more. Let's do one more. Just to make you do more. Because I didn't see too many raised hands. Very quick. Product of numbers in a linked list. Product. Imagine none of the numbers is 0. Okay. So let's pretend none of the numbers is 0. So product of all numbers in a list and assume none of the numbers are 0. Okay, let's run it once. Let's run it once. So see out L.sum L.hptr and end it. Okay, I'm just showing you this. I'm running it and showing you. You can also try if you want. What's the tempo. So we'll run it and show you. Still some cannot be used as a function. Why? Huh? Sorry, what's the problem? Acha. Okay. I used it as a variable also. I should not use it as a variable, no. If I'm And that's why you call the function as get sum. Don't call it sum. Now look at the, we should have given a space. Anyway, it doesn't matter. Okay. See out sum of elements. Okay. Yeah. So the sum of elements, as you can see, is 50, 60, 65. Okay? So it works for us. Sum of elements. Did you get it? I want all of you to get it, please. Now, use our code and write product. Product of elements. Using recursion, no loops. Over? Good. Product. You say get product or product, whatever you want to call it. Same, it takes a pointer to the head and builds the product of the list. Product of all the elements in the list. What will it do? Again, it has to use recursion. Very similar to this. How many finished product? Please think a little, you will get it. Write a function called getProduct, which will take a node pointer, that is the head of the list, and produce a product of the numbers. Assume all numbers are non-zero. Think in the same way. If you have to have a product of 10 elements, it is product of the first element and the product of the remaining 9. Keep on thinking in a similar way till you reach a list of one element. If your list has only one element, what is the product? The same element. If you have a list of only 10, one element, 10, product is also 10, same element. Okay, we'll wait 2 minutes and then we'll solve. Okay, so just bear with me, I'm solving it. So we'll call it int get sum, get product. And same starting pointer, node start temp. We'll call it again with hptr. Yeah. So yes, so we have get product. How will we do? So if we are assuming nothing is zero. So if it is a single element list, how do you detect? Temps next equal null. So if it is single element list, temps data is the list. So we return that. Else we will return what? This guy's data into the remaining list, whatever it produces. Correct? Product of 10 elements is product of one element and product of remaining 9 elements. So we say return temp.data into get product of temps next. Whatever is there in the list, remaining list. Remaining list is what? Temps next. That is the remaining list. Remaining list into this first node. Okay. So that is the product. In case it's the so we will try to present that.
Recursive display.
Yeah. So, oh, such a nice round number. So that is the product of the list. I think you got the same answer. Shall we move? Everybody clear how we got product? Same way we got sum. Instead of adding, we multiply. Okay, let's try something else. Okay. Are we ready? Now, I want to search in a list for a particular element without loops, that is using recursion. And it should respond by saying yes or no. I mean, the element is there in the list or found, not found. Okay, I'll make it simple. Okay, I'll make it even more simple. Instead of returning found, not found, I'll say if it is there, return 100. Okay, making it that. Or if it is there, return some number. You can return the same element also, it doesn't matter. And if it is not there, return a minus 1. I'll assume all elements are positive. If it is there, return that number. And if it is not there, give me a minus 1. So write a function which takes two parameters. What are the two parameters? Head of the list and the number you are looking for. Or find should take two parameters. Head of the list and number it is looking for. And it should give me, if it is there in the list, it should give me the number back. Yes. And if it is not there in the list, it should give me a minus 1. You have to use recursion. The thing called find takes two parameters, head of the list and the number. It should give me back one of two things. If the number is there in the list, give me that number. If it is not there anywhere in the list, give me a minus 1. Make sense? No loops. No loops. Yeah, let me start writing it. As I said, I am going to take two parameters. And its return is an int. So I am going to say int find. The two parameters are node star temp, some head pointer of some kind, and int the element that I am seeking, I am looking at. Now, in this case, we have to, as usual, look at the terminating condition of a list. So, if temps next is equal to null, that is, I am looking at the proverbial single node list. If I am looking at a single node list, I can give, imagine I have a single node list. Imagine that I have been given a number. With a single node list, if the value which I am given, E, corresponds to my data, I will return that data. Else, I will return a minus 1. Answer is solved there. There is no more recursion. I will not call any more recursion. It will be solved here because there is nothing more remaining in the list. I have reached the fag end of the list. So, I will say if temps data equal E, then I say return either temp data or E. It's one and the same. Else temps data is not equal to E and I am on the last node. So I will have to say else return minus 1. Okay. This is my first, this is the end of this bracket. So, sorry, not of end of this bracket. So, everybody clear with this part? Imagine, remember, how do I handle a trivial condition? My list consists of only one piece. Okay? If my list consists of only one piece, and how do I check whether it consists of one piece? You know the obvious check. Temps next is null. That is why end of my list. Right? That is always the end of my list. So if that is the only list that I have, then I have no other option but to compare E against the data. And if it matches, very good, I return that data. And if it doesn't, so be it. I return a minus one because I can't do anything else. I have one word list at the moment. If I have a one word list, I have to make a decision right there. There is no question of going further. There is nothing to look. I have reached the end. That is what I have indicated. Temp next is equal null. We are at the last point. And we are there. And we are having the element we are looking for. So we just say we are done. Right? Else. Else means the list is not end. We are not at the end of the list. So what will I do? I will now do checking with the head of the list which I have. So let me write the else part. Okay. So let me write else. Okay. Let me write it on the next page. This is the else part, please. Else part. So I have a temp and I have a element. So I will check if temps data. Now I am on the first node of 10 nodes, let's say. I am checking whether the first node itself matches the data or not. So temps data equal E. Oh, fantastic. I got a match. In that case, again I say return E. End of the story. Else. Remember, this part itself is in the else. Else. Else, what does it mean? When do I come here? When I have more than one node in the list and the first node in the list is not equal to what I am looking for. What should I do? What should I do? I am having more than one node in my list and the first node in my list doesn't seem to match the element that I am seeking. What should I do? I should hand over, no? I should call whatever my find is going to give, that is what I am going to give back. Now I can't do anything. So now I have reduced the problem by one part and I have to delegate that problem to the remaining part. So I will say return find of what? Temp next. Correct? The remaining part of the list. Temp next E. Whatever that gives me is going to be my solution because I am not matching. If I was matching, I am the head of the list. I am matching, I would have given the answer. I am not matching. So my whatever the answer will come from the remaining part of the list is going to be my answer. Can't be anything else. Either I have to match myself or I have to delegate the answer to the remaining part. That is, let the remaining part of the list be handled. So what will I say? Else return find temp next comma E. I can't do anything else, isn't it? What can I do? This delegation little more clever. Yes? Okay. Let's see whether this goes. We'll type in the code. So int find. Okay, find element. Takes two parameters, node star temp and the data that I am looking for in the list. Check again the terminal condition. If the list contains one element only, how will I answer the question? And how do I identify? Temp next equal null. If my list consists of just one element at the end, then what do? I just compare that element. If temp data, if temp's data is equal to that element, E, then I say return E, because that's the way we are behaving. The element is there, we return that element. And else, okay, this else. That is, I consist of only one element. My list is only one element, one node, and it is not matching. Answer is very simple. Return -1. Think of that problem. It's a single node problem. Single node, either you match it or you give a -1. Else, return -1. Okay, now this else is when there are more nodes in the list. More than one node in the list. So what do? I compare the head of the list, which is temp. I compare temp's data with that element. Can be same. Okay. If temp's data equal E, I'm done. Then I say return E. I found it at the head. Okay. Now I have more nodes in the list and the head is not matching. So now I have to work with the remaining list, and whatever that gives me the answer, I will return that as my answer. So else return find element temp's next and E. Yes. And at, I think we have taken all conditions, but I don't think we have missed any. Okay, let's see. So we will do find. What is our list? 15, 10 something. 5, 10, 15, 20. Okay, 10, 20. So see out here. L dot find element L dot HPTR, and we are going to find the value 10, comma 10, end. So since 10 is there in the list, it should return back 10. So let's try a value 35. So we will change it and we'll say there 35. So we are looking for a value 35 in the list, and we'll try it again. Okay, you see it produced a -1 because 35 doesn't exist in the list. Everybody with me? No, yes. Is it coming in? The recursion. Okay. Okay. One for the road, as they say, right? You know how one for the road is used? Very easy. Length of a list using recursion. That is how many nodes are there in the list. You don't know. You only know the HPTR. Forget the count. Let's say I don't give you the count. So take the head of the list only as a parameter and give me the number of nodes in a list. Are there 5, 8, 15? How many nodes are there in the list? Give me that without doing any loops. You are given only the head of the list. You have to tell me how many nodes are there in a list using recursion. Not yet. Good. Count it. The corollary of the similar problems, what we did so far. Just think through. So write a function called getLength. Takes only one parameter, the head of the list. Yeah, tell me. I can see your code. What's the number?
Shows segmentation since last.
Still doesn't matter. You have saved it, huh? What's the number? Number.
565.
565. 565. Last. Get length. Where is your get length? What's the name?
Nums. NUMS.
NUMS. Return is not a function, no? Return, in that case, nums of temp next plus 1, no? Just change that to, first of all, plus 1. That's all, no? Length of the remaining list plus this guy. Correct. Good catch. Somebody has already. We don't need that temp, HPTR, count and all that. So it's called it nums, no problem. So if the list consists of only one node, what is the length? Length is 1. No brainer, right? Return if temp next is null, that means this is the only node now left in the list. Answer is 1. Else means there are more than one node in the list. So what is the answer? Length of the remaining part of the list plus this guy, the head guy, right? Plus 1. That's it. So that's the answer. As simple as that. Okay. So we can give you our version. Okay. Okay. For those of you who want to revise it to this point. Okay. Those of you who want to take our code as 5, as a practice lab 5, and work with it at home. You just have to log in same way as you do it. So we close everything at the night. What time do we close? 10 o'clock. From the time you reach home till 10 o'clock it is open. Then it cleanses itself and goes to the next day. Situation come there. Okay. So far for the first next few weeks we'll limit it to 10 o'clock. Another thing is we have started putting it on KMIT Vista. Some of you may have seen it, may not have seen it. It's lagging a bit. Lagging means older sessions are available. The immediate sessions